In this question, we are asked which of the following is not a characteristic of the X-ray spectrum. Okay, when you fire electrons at the target matter. Okay, so first statement, right? The range of wavelength is continuous. Yep, this is true. Why is it continuous? Because you got to understand, right? What's the mechanism? So we have the nucleus here. This is the nucleus of the target matter, and there are many of them. Okay. So incoming electrons, right, they move near the nucleus, okay, got decelerated and lose Ke. So loses energy. How does it lose energy? It loses energy, right, by giving out a photon, okay. So this is a photon, but how energetic is this photon? We got to go back to the energy of the electron to understand this. So this electron, right, gain energy because we apply a accelerating voltage, and this is equals to V E times VACC, or accelerating voltage. This is typically, right, maybe more than 10, okay, KE, more than 10 kV. Therefore, right, this electron will have more than 10 keV. So he has a lot of energy. So every time he goes near the nucleus, he'll lose a fraction of it. So a fraction of a large amount is definitely, right, sizable, okay, and usually of a same order of magnitude. So you just think about it as a millionaire going to a casino and gamble. So each time he plays a game, loses some money, it will definitely not be $1, $2, okay, because it must be proportional to his status as a millionaire, right? He brings a lot of money to the game. So same for the electron, he must have lost quite a lot of energy. So this caused, right, the photon emitted to be X-ray, yeah. And so, right, you see these electrons, all the electrons that fire the matter, they could lose any amount of energy because there's no rule saying how much you can lose. Therefore, right, all these X-ray photons produced will be can be of any energy. That's why we see a continuous spectrum. Okay, and that's the bremsstrahlung here that we're talking about. Next, right, the minimum wavelength is dependent on the target matter. Okay, so why do we have a minimum wavelength here? It's because, right, there could be a chance that this electron is quite unlucky to lose all its energy at one go. So the first encounter with a nucleus, he loses all his energy. So that will mean, right, so loss in Ke equals to the Hc over lambda of the photon. Since we lost everything, okay, this photon will be the most energetic, so this lambda will have been the smallest. That's why, right, there's a lambda minimum. We can see from this equation, right, the only thing that this lambda minimum depends on is the accelerating voltage, is how much Ke you gave this electron in the first place. Okay, so it's not dependent on the matter. So this statement is actually wrong already. Okay, and it is dependent on the accelerating voltage. So C is correct. Finally, let's just round it up by looking at D. When you fire more electrons on the target matter per unit time, you are so to speak, right, you are transferring more energy per unit time, right? More energy of what? Is more Ke of electrons into, finally, right, X-ray being emitted. So if you fire more electrons, okay, then, right, you will expect that this entire curve, right, will bulge upwards, okay, because you have more electrons losing energy at every particular wavelength possible. Okay, so this is if, right, number of electron increase, okay, number of electron per unit time increase. However, right, the more common scenario that we see is usually, right, what if you increase the accelerating voltage? Then you'll see this curve, right, increase instead. Shift to the left, resulting in a smaller lambda minimum. Okay, and the whole curve also bulge up. Okay, because, right, when you have the electrons being accelerated with a larger voltage, they carry more energy to the metal, they will lose more energy and give out more photons. Okay, therefore the entire spectrum will also rise. You can think about it as the whole tide is rising. Yeah, the whole water level is rising.